Reversing and exploiting an Apple firmware update. Okay, so this is the situation that we're in. I'm assuming that you've already compromised a Mac OS X box. This is not like a new method for penetrating a Macintosh. So you've rooted somebody's box. Say you read the book by Miller and Diazovi, which is a great book. You found some 0-day and you exploited somebody, and you want to maintain control of this box. So this guy, Jesse Daguano, he presented a talk on OS X rootkits at Black Hat last year. And so you could use his proof of concept rootkit. There isn't much work on rootkits on Mac OS X. Nemo did some stuff a long time ago on older versions of Mac OS X. Just recently at DEF CON, I guess his name was Bose Erickson. He did runtime kernel patching of the sysint table. But there really isn't a whole lot of publicly available rootkits on Mac OS X. But one thing that all these things share in common is that if the user reinstalls the operating system, those rootkits die. They go away. So the thing is, we want to maintain control permanently. So suppose whatever vulnerability we used to get access to the box in the first place, Apple releases a patch, and if the person that we exploited, they're very paranoid and they reinstall the operating system from media, and they safely update the patch level, we want to still, once we've gained access, we want to permanently have access. So how are we going to do that? Well, there are some things that work to our advantage. What Apple does is they like to release products before they've been fully tested. What they do is they use the early adopters as basically as beta testers. And then what they do is the products aren't quite ready, but they're shipped. And then they later address bugs and issues with firmware updates. And a few months ago, I went to support.apple.com, and I did a search for firmware update. And at that time, there was almost 1,000 firmware updates available. So that's quite a large number of firmware updates. And one convenient thing about the Mac world is that the Macs, they don't tend to change all that much. Like a lot of machines, they're, hardware-wise, they're quite similar. Whereas in the PC world, things are quite different. Like a Dell and an Acer and HP, these machines are underneath are actually quite different. So this is just to kind of show you on support.apple.com. If you do a search for firmware update, there's all kinds of stuff. So what kind of stuff has Apple issued firmware updates for? They've issued firmware updates for graphics cards, keyboards, trackpads, the Bluetooth adapter, all these things. So what we're going to do is we're going to look at the keyboard. So what can an attacker do when they have control of your keyboard? They can pretty much do whatever they want on your machine if they control your keyboard. So this is a picture of a dog just kind of typing at a keyboard. There's an old expression, what is it? Nobody on the internet, nobody knows that you're a dog, whatever. Okay, so if the attacker has control of the keyboard, what can they do? What they can do is they can literally shovel a shell back to themselves. So how do we do this in Mac OS X? We can use Spotlight. Spotlight is by default, installed on Leopard and Snow Leopard. So you type command space, and that activates Spotlight. And the focus is automatically in that box. So you can type terminal, press return, you launch terminal.app, and then you can type that sequence of keys, exec, bind, shell, and so forth, where you replace IP by the attacker's IP and port by the attacker's port number, and then you press return. And what does this do? This literally shovels a shell right back to the attacker. So you can have like a netcat listener, and then you can just literally control that computer. So if somebody has control of your keyboard, that's not a good thing. And some Mac users, they think they're protected because they use some outbound, personal firewall. And this Little Snitch, which is a pretty popular product. This doesn't do anything. You can just add, in that keystroke sequence, you can just add a return. And the default option for Little Snitch is just to let the network connection go outbound. So what can we do? If we control the keyboard, what can we do? We can persist the rootkit. So say if our rootkit on this guy's machine is eliminated. The user reinstalls the operating system. What we can do is every time the machine boots, we can actually signal to the keyboard, that we're still running. And then that's say using the control USB endpoint. But at some point, if the rootkit has died and the keyboard no longer receives that signal, then the keyboard knows that it needs to send control back to the attacker. So we can keep a rootkit alive even if the host operating system is reinstalled. And the reason why I have a picture of this guy, Terry O'Quinn, is that he plays, I think his name is John Locke on the TV show Lost. And I don't know if that show is popular around in Europe. In any case. Okay. So the keyboards that Apple currently sells, there's 3 varieties. There's like the top keyboard is like a full, like a USB keyboard. It came out in August 2007, and it's about $50. And then they have a Bluetooth keyboard that they came out with at the same time. That's $79. And these are very thin, like aluminum keyboards. And then in March 2009, they came out with a smaller, like a USB keyboard. And just recently, like within the last couple of weeks, they updated the Bluetooth keyboard. Now the older Bluetooth keyboard took like 3 AA batteries, and now it takes like 2 AA batteries. And I don't know what other changes they've made because I haven't had a chance to really look at it. But as far as I can tell, that top keyboard is the most popular external keyboard because it comes by default with like the Mac Pro, the iMac, and it's the cheapest. I think now the default options have changed, but there's quite a period of years where that was like the default keyboard that came with a Mac, a desktop Mac, that is. So we're going to focus our attention on that keyboard. All right. But in 2007, when Apple issued that keyboard the keyboard had bugs in it, believe it or not. There were problems with it. And on Apple support forums, you can still find some posts where people are complaining about various bugs in the keyboard firmware. So like, keys would keystrokes would be missing and various, problems that they had. So this one, it misses like 1 in every dozen keystrokes. So Apple didn't test this product when they released it. So what did they do? In April 2008, they issued a keyboard firmware update. This is the first time I've ever heard of a keyboard firmware update. But in any case, so they issued this thing, and this is the URL that you can go to download it. The only thing is recently Apple changed this. Sometime between my presentation at Black Hat and TourCon, they changed it. But if you want to get a copy of the original, contact me afterwards. So the original firmware update, it's this .dmg file with that SHA-1 hash. You download it and say copy it to your desktop. That you mount that DMG file, and there's like a .pkg file. And if you double-click that .pkg file, most likely, if you have a keyboard attached, this is the message that will come up if you apply all your patches and so forth. So there's a check in there that whether or not the keyboard has already been updated. But it doesn't matter, we can bypass that. So if you have the Xcode suite of tools installed, you can use this tool, Flat Package Editor, and look inside of .pkg files. You can also use a tool, a shareware tool called Pacifist. So within there, that PKG file, there are 2 other .pkg files. One is for the aluminum keyboard firmware update, and the other one's for the Bluetooth keyboard. So the first one there, that's for the aluminum the external USB keyboard. So take that payload file and drag it to the desktop. And if we double click that, then what happens is there's an applications utility, applications directory is created. Within that, there's a utilities directory, and then within that, there's a Cocoa application. And what the installer does is it takes that payload and actually runs it in the root directory, but since we copied it to the desktop, it's created on the desktop. So if you run that Cocoa application, that thing also checks if the keyboard needs to be updated, and if your keyboard has been updated, it refuses to do anything. So the only option there was just to quit. So now what we want to do is, we can look at that Cocoa application. So if we right-click and do Show Package Contents, in Mac OS X, an application is actually a directory with a whole bunch of stuff in it. And so here, there's a contents directory in Mac OS X. That aluminum keyboard firmware update, that's the actual binary. And then there's a resource directory, there's a plist file, and all this other stuff. So if you want to, learn more about having, if you want to have an introduction to reversing on Mac OS X, I recommend Cameron Hotchkiss' Recon presentation. Okay, so let's look inside that resources directory, and there's a whole bunch of stuff in there. There's a localization languages, and All right, so if we look at the thing that was in the contents Mac OS directory, this Illumin keyboard firmware update, and we look at its magic number, it's Cafe Babe, and in Mac OS X, that's like the magic number for a universal FAT binary. So we're going to look at the x86 binary. So, there's a tool that called LiPo that you can use to like separate the two. That's kind of an aside. So in terms of like when a keyboard is plugged in, there's a tool that in the Xcode suite of tools that's pretty convenient, and that's IO Registry Explorer. So you can look at devices on the USB bus, and I don't know if you can read this back there, but it gives information about like the the vendor ID, product ID, and all kinds of various things. So kind of like from a high-level view, if we look at these values for like an updated keyboard, there's this BCD device value, ID, product ID, and vendor ID. So Apple's vendor ID is a 05AC, and the US USB keyboard, this thing has a product ID of 0220. And whenever it's been updated, the BCD device value is hex 69, but whenever it hasn't been updated, it's hex 67. So this is the mechanism by which they can tell that the keyboard has been, whether or not it's been updated or not. That's kind of like a revision number, so to speak. So, and if we look at the output of USB view on Windows, this keyboard it has 2 interrupt in endpoints, and the first interrupt in endpoint has a max packet size of 8, and the B interval values for both of them are hex A, so that's like 10 milliseconds. So every 10 milliseconds, these, the host is like querying the keyboard. Okay, so in terms of like tools, in order to disassemble the binary, I just used OTX. Could have used IDA Pro. I don't have a license for IDA Pro. To do binary editing, I use this tool called ED. Okay, and one thing is, I'm not sure if people here are familiar, there's this law in the United States called the DMCA, the Digital Millennium Copyright Act. And this can make like reverse engineering kind of difficult in the US. But one of the things is there's an exception in the law. So if you have if some company has some software product and then you independently create your own software product, then in order to make your independent software product interoperable with this other company's product, you're allowed to do reverse engineering for the purpose of interoperability. So what I've done is I've created a Trojan for Apple's keyboard. And in order to make sure that this Trojan is interoperable with Apple's keyboard, I need to do reverse engineering. So there's no DMCA violation here. Okay. All right, so now we're going to step into reverse engineering. So that Cocoa application was checking that the keyboard, whether or not it had been updated or not. So there's like this delegate method, application did finish launching, and this thing does like a number of things. It checks the operating system version. It uses the IOKit framework to like find like the attached keyboard. It checks like the validity of this firmware image file that's in the application bundle. And it uses this function that Apple calls CRC32. So just for kicks, why don't we take a quick look at this function CRC32? So here, this is a disassembly of this function CRC32. You see the function prologue, ESI and EBX are saved. 16 bytes are allocated on the stack. So the thing is, the argument to this thing is an NSData object. There's some class method in NSData, and that is the pass like the actual that firmware image file. And there's message passing in Objective-C, so it's like we get length. Length is called on that thing, and the return value you can see is put into ESI, and then bytes is called on that file, that firmware image file, and that is put into EBX, and then like ECX, EDX, those things are cleared. So there's a very short little loop. So you can see that EDX is kind of used as a counter. And ECX is like kind of accumulating like the values in the file. So then we just keep on checking whether or not that counter finally reaches the length of the file. And when it does, then what ECX has is it has like the sum of all the bytes in the file. So is this CRC32? This is not CRC32, right? This is not even close. So this gives you some idea of like the quality of Apple's code. They just did not understand what CRC32 is, and they didn't implement it correctly. Okay. So in any case, so whenever we were trying to like run the updater, there was a number of places where the version, the firmware version was checked, so we had to patch the binary to disable those checks. So in a number of places, so this is a couple places. So here we make both of those jumps unconditional. Another place, no op that conditional jump. So now those we've disabled the various version checks, and this is what that Cocoa application looks like whenever you plug in a keyboard that hasn't been updated. This is what it looks like. And then what you do is you click that. It has like a couple things, like make sure the power cord is plugged in, all this thing. Make sure there's only one keyboard. And when you click that update button, then there's an error message. So there's yet another place where the version is being checked. So we need to look inside the nib file. So if you're familiar with Mac OS X, the nib file encapsulates the user interface of an application. So recently, like within the last year or so, Apple's changed it to like .xib. Now they're .zip files. But in any case, so if we look at that nib file, in the Xcode suite of tools, there's this tool called Interface Builder, and that's used to lay out applications in Mac OS X. So this is a very simple layout. There's just like that one window, and there's that update button. But in any case, we can, looking at the .nib file, we can figure out exactly what code is called when you press that update button. So that little inspector tells you that do update in my main controller. That's what's called. So if we look at that do update routine, like in my main controller, it does like a number of things. It checks that the machine is plugged in. It asks for administrator privileges. Actually, administrator privileges are not, up until the recent security update, administrator privileges was not required to change the firmware update on an Apple keyboard. But I disclosed to Apple at Black Hat that there was a bug in IOKit, so they recently fixed it. So now you do actually need administrative privileges. Before you didn't. So what that Cocoa application is just a wrapper around this tool, HID Firmware Updater tool, like in the application bundle. Like that Cocoa application just asynchronously calls this thing. And it calls it twice, with like the first time with that dash parse argument, and the second time with those arguments. So if we look at this HID Firmware Updater tool, it doesn't have any symbol information. And this is the third place where it checks the keyboard version. It looks at the BCD device, and it won't do anything if it's greater than or equal to hex 68. So, but we can disable that. That's not a problem. So we just no-op that jump of above instruction. And then now we can actually flash the keyboard. We can just re-flash it to like the current version of the firmware. Because I'm going to be pressed for time, I'll do demos. I'll do a demo at the end. Okay. So if we look at that firmware file, it's if we look at say the first 32 bytes, this thing is obfuscated by Apple. You can look at that thing. That's just it's kind of nonsensical. But what Apple did was they basically just screwed up. So what happens is that firmware image file, it's de-obfuscated on the machine, and then whenever you're doing the firmware update, the unobfuscated firmware image is sent over the USB bus to the keyboard. So what we can do is, the HID firmware updater tool does this de-obfuscation for us. So that's very convenient. So what we can do is, we've taken over a Mac, we take this obfuscated firmware image from file from Apple, then we can, because that thing, the HID firmware updater tool unobfuscates it for us, what we can do is we can set a breakpoint at an appropriate place. Like we attach a debugger to that HID firmware updater tool, set a breakpoint at the appropriate place, and then modify that firmware image file in memory, and then send the, basically add our Trojan there, and then send the Trojan firmware image file to the keyboard. And when we do that, then we also own the keyboard too. Okay, so let's take a quick look at how Apple did the obfuscation. It's just terribly done. It's just hilarious. So let A be this 83-byte sequence, and let B be this 53-byte sequence. Then this is what the de-obfuscation algorithm starts off with. It reads like the firmware image file, like an 83-byte blocks, and then it does this thing. And then it does further stuff. This is not cryptographic, obviously. It's It's just some crappy obfuscation algorithm that they came up with. And okay, so I won't discuss that thing further. It's just they just did a crappy job. So, and it's a truism in computer security, don't do security through obscurity, but that's exactly what Apple did. So this is a screen grab from the movie Office Space. Hopefully everybody has seen this movie. So, okay. So, so we can take that unobfuscated firmware out of memory very easily when we're running this tool. So we attach GDB to that tool, set a breakpoint at that address, and then whenever we run it with those arguments, then we can just dump the unobfuscated firmware out of memory very easily. So this is what it looks like. This looks a little bit more regular if you see this red. So I'll explain exactly how this thing is like formatted. What it does is there's like 3 bytes followed by 32 bytes, 3 bytes followed by 32 bytes, and so forth. So, okay, so now we need to figure out how does this firmware update get sent to the keyboard in the first place. So the keyboard, it doesn't have an interrupt out endpoint. It only has like a control endpoint, endpoint 0, and then it has like these 2 interrupting endpoints. There's no out endpoint, so there's no way that the host can, it doesn't use the interrupt endpoints to send the firmware image. What it does is it has to use the control endpoint. And that function in HID firmware update, hex 20C3 does it. And what it does is it calls this, in IO USB device class, it calls that routine. So luckily, what we can do is we can just set a breakpoint there and then just look at the arguments and then figure out what's going on. Because what I don't have is I don't have like a USB analyzer, so, okay. So we attach GDB, set a breakpoint there, run, and then we can look at the arguments. And we can go to opensource.apple.com, look at this USB, the source, their USB stack. And so we look at this struct for the IO USB dev request. We can like pick this thing apart. So this BM request is hex 21, then there's a B request. This is like, if you look at the USB standard, this is like a set _ report request. Then the next thing is this W value, and has these values. This index value is 0. The length is just 1, and then the actual data that's just sent is just hex A. And so in order to put the keyboard into like a bootloader mode, what you do is you just send like a set report to the keyboard, to the control endpoint with these values. And then what happens is that the keyboard, it was originally a keyboard, and then it drops off the USB bus, and then it re-enumerates as this keyboard bootloader. So, okay, and this is a little bit hard to see. This is the output of a USB prober, I think is the name of the application. So it has like, it has an interrupt in and out endpoint.